they're known for the determination of the figure of the Earth, meridian arcs. So measuring the length of the meridian, how would you do that? Determine the difference in latitude between the points, and then you calculate the curvature. That's how you do it. Calculate that curvature hard. So never been measured, still never been measured, using the coordinate system, never been substantiated, arbitrarily assumed, calculated, ratioed against everything. That's where we're at. If we quickly revisit our boy Eratosthenes, and we had a question about how he knew the distance between Syene and Alexandria, well, turns out by knowing the distance, it was measured by professional surveyors called bimatists. Okay, so he had his own form of geodesic surveying, and they had obviously known by calculating to their held spheroidal models what that distance between those two cities was for sure. So all of that, of course, means that we know we're on a globe for sure. Everything is coming up globe, and it's like, well, no, have you met the graticule? The graticule being the spherical network that people get confused with the globe all the time. They say that it's on map projections, right? Well, no. Maps are projected coordinate systems. What coordinate system are they projecting? The geographic coordinates, forever and always. As Alan kindly pointed out earlier, there was a decree royally put forth that only these coordinates shall henceforth be used, and this is all we've ever seen. This is all the world maps ever would be allowed to input-output. And again, it's not a map projection itself. It is a set of spherical coordinates used to reference positions on the Earth. So again, latitude and longitude are not a map projection. They are themselves the backbone to what is projected into maps. So we're going to briefly cover our datums, WGS 84, NAD 1927, NAD 83. These are all spherical geoidal datums, right? So spherical geoidal datum in, spherical geoidal datum out. That's what this is going to show. Garbage in, garbage out. No matter what you're dealing with, it's input in the model. It's going to be output in the model. We're going to touch briefly on the Gleason's map and how it's going to be used to ratio our terrestrial meridian to find distances between places. But just know that all maps are projecting the graticule, that spherical network of long lat. I think it's important to point out that globers don't actually know that maps are distorted, right? They're distorted because they're projecting the spherical graticule, also known as the celestial sphere, because it's a one-for-one copy, not because the Earth is a sphere. Because even by its own definition, it's projecting a spherical coordinate system. The goal would be to prove that this is, in fact, the Earth and not a projected coordinate system, which you will not be able to do because everyone will admit this is a projected graticule. It's a spherical graticule of longitude, latitude. So then the goal would become to prove that the graticule relates to the Earth, right? So that's where geodetic surveying comes in, where they relate those astronomical coordinates to geodetic coordinates, and they try to make it to the Earth. Now that's all kind of fluffed and standardized and corrected to hell, meaning that this spherical datum has never been proved to be the Earth. This has always been the graticule. It is literally a model, conceptually idealized, created from angles to the stars. One of our favorite depictions of said model, though, is in Gleason's map, also known as an azimuthal equidistant projection. Some people would think that this has hence been debunked or discredited, but in actuality, because of its basis as a projected coordinate system, you can no better discredit one projection than you can the other. If a Mercator works, then so does an azimuthal, so does an equal area, so does an equal area cylindrical, so does a Bullitt-Myers. It doesn't matter. You can't discredit one without discrediting them all, as they're all from the same projected coordinate system. So when we use the Gleason's map, right, it is a true direction or azimuthal projection, meaning it's preserving the direction of specified points on a great circle. Very important to note. And then they say that the great arcs are rectified or shown as straight lines. So that would be, if we were to show what our great arc was before, here, I'll definitely get into this. Where's my GeoGebra model showing what we were measuring at 6214? I think it was right here. So if we look at this, on a Gleason's map, this distance right here that we're looking at, this 6,214, if we put it right here, this from the North Pole to the equator, right, 6,214 miles, this curved distance gets straightened out and represented linearly correctly, meaning that from here to here is the same curved distance, except now it's straight and it still represents the same amount. That is an aspect of a direction preserving map, meaning it's a facet of the tool that we're using to straighten out those great circle arcs. So when they're saying you can't have great circles on flat Earth, it's like, well, have you heard of the azimuthal equidistant projection? Because our boy Alex Gleason certainly has, right? And he put it out there with some instructions on how to use it. Unfortunately, no one read these instructions, and they try to use the given rulers in the ways that they're taught, which unfortunately, pollutes the projection and doesn't use it correctly. Real quick, when you get this map, it comes with these two rotator arms. I think they're called articulator arms or whatever. We're just going to call them rotator arms. They are meant for the different measures of scale that are on the bottom. This right here and this apply to this and to this, right? And they're used to measure outward from the center, which is, again, very key because that's how we can preserve our great circles, right? This great circle here out is the same because it's flattened out. And again, it comes with these, I'll call them modular arms. And it also comes with instructions on how to use said arms, right? And it says, based on his own words, he said, within the map are circulator lines from the North Pole. You have indicated by the letter G, and you have indicating arm. Put it in the center. It goes along a receptacle. It can then rotate outward. So he calls it a longitude and time calculator because you can calculate the longitude from the time. You can determine the time with the map itself. So you can determine what time it is anywhere else using these rotator arms, right? And that's why he calls it a longitude and time calculator. And it's based on the Greenwich meridian, right, running through the line of 0 of longitude. And from there, as long as you use the relationship of 15 degrees per hour, which we all know and should be familiar with, then you get a representation of a relationship. 4 minutes times 1 degree with 15 arcs of longitude. So 15 arc seconds would be 4 minutes. And we can use that relationship to properly understand where the positions are. So he gives an example of how to use it here, dividing it between 4 circles. We can use a different example here. Let's just say, let's see, let's look at the conversions here. So each degree of longitude is 4 minutes of time. Because of that 360-degree relationship we went over earlier, when we're looking at the map, you can divide it into 15 degrees per hour into 24 sections to get the 360 degrees of your circle. And you can know that when you measure the angle of these degrees, then you get the difference. So how that would work is you would line up this arm, say, with New York over here, and this arm with, I don't know, whatever this South American country is over here, and you would physically measure the angle that these two arms create, and you would use that to determine the time. So let's just say, let's see here. If it gets like 12 degrees, you multiply that and you get the distance between these two. So if you do that, then the local time is ahead of Greenwich, and then the other time is behind it. So they do east-west, and they do positive and negative features for that. What gets confusing for people, I think, is that on the bottom of the Gleason's map is the scale. So people tend to look at the scale and then start trying to apply it all over the map and try to measure things and try to make it work. That doesn't quite work that way, right? It's a time longitude scale, right? So they're using the bottom one to comport longitude to 1 hour of sun time, and then each degree of longitude to 4 minutes of sun time. And the top one is a 69 miles per degree scale meant to be applied from the center outward. So then would you use the map, right? Actually, let's go over this. Example for an application would be if you to measure a distance of 90 miles, and that would correspond with 1.5 degrees of longitude at the equator. And then those 1.5 degrees would be multiplied to get sun time. And then you use the difference to determine where the time is at that location. So the time gets crucial to determining longitude because it just gets equated to degrees. Now, if we were to see how people want to use this scale, like they get this map, they try to look this and they say, look, this doesn't work. It's broken. Show me a map with a real scale. And it's like, well, if you were to use the tool correctly and understand the coordinate system with which it scales and how it straightens out great circles, meridian arcs, etc., you'd apply it just like this. This scale would line up neatly. You'd measure outward from the center, 69 miles per degree, as we went over before. The other way to do it is, of course, longitude and time calculator. So we can determine a time difference using this, right? If we know New York and Tokyo, we can get the time difference between the two. And then we can use that difference. We can convert the longitude difference to time using the 15 degrees per 1 hour, half hour angle calculation. What it would look like in practice is this. we would place one arm at Greenwich, London, right at 0. We'd place the second arm at New York, and that would create an angle of 74 degrees. We'd measure that between the arms, right? This would be a 74-degree angle. This isn't representing that, but it would be something like this, right? That would be 74 degrees. We get the timing difference. 74 degrees times 4 minutes over 1 degree would give us a difference of 296 minutes, which is roughly 4 hours, or just under 5 hours. So they say, hey, if it's 12, then it's actually 7:04 a.m. in New York. From that, you can use to get an actual difference in distance, and you can use that longitude to calculate at that scale, 69 miles per degree, to get the distance between the two. So when people say the Gleason's map doesn't work, no, it exactly works. It computes distances between the coordinate system, right? A good way to look at it is the distance isn't determined by the visual scale. It's determined by the gridded network of longitude and latitude behind it. Real quick, we can look into this video. I think it has sound, but we don't need sound. This was put forth real quick as a tool on someone misunderstanding the Gleason's map and trying to get us with a gotcha for the sun. And the sun in particular can be tricky unless you can apply it correctly, right? So right off the bat, a Glober put this out and was like, look, first of all, the sun angles don't work. All you guys are at different spots on your flat earth dirt pizza, right? And the sun's over here and nobody can see it in the right spot. First of all, right, if you're drawing straight lines on this azimuth Euclidean projection, that is incorrect. This is not a eastward vector, right? This is east and west are circles. If this is going straight, I don't know what direction he's looking, but it isn't where the sun is. So that's a common misconception. People use straight lines on the Gleasons. That cannot work. When we get into it, we actually we put a observer focused azimuthal grid over each observer, and then we can see that only will that make the sun observed azimuth make sense when you have a limit of spherical view above you, right? When you're trying to use this projection as a tool, be aware of its inherent distortions when trying to show things, right? I myself use it all the time for sure, but I'm very conscious of how it gets distorted and how to use it. So if you're displaying things, right, you can know that Australia isn't this size. Obviously, it's an aspect of this projection straightening out its meridians and distortion inherent from the center escalating outward. So we know that, and we can use this tool anyway by moving it further out here than we would in here to represent the same distance. So we're not saying we're moving further. We're saying that we know the distance scale is skewed. So using it for the sun, though, cool. So right about here, we go into mimic each observer-centric position. So we, instead of doing these straight lines orthographically drawing on this map like a retard, we can go and do actual application of tools. We can preserve the direction-preserving aspect of this azimuthal equidistant projection. We know that it currently is only preserving directions from the center. It preserves directions from the center point. You could technically make a new azimuthal equidistant projection for each one of these points, but we're just going to move this azimuthal grid and use the observer focus part of it. So again, we're going to focus in on one of our observers using our grid and this map, and we can see, oh, exactly where the sun is where this observer claims to see it once we utilize the tool correctly. All right, we do the same thing with our other observers. I think this one as well comes right in here. So go to this.
Real quick, this looks kind of confusing because we have like the true position of the sun overhead representing its GP, right? And versus how we see it in our local azimuthal grid. So it almost looks like, there's two suns, or you would see something differently or whatever. But what all anyone ever sees is what's in their azimuthal grid, which corresponds to a ground position. But that is how you perceive it. There wouldn't be like a difference between the two. You know what I'm saying? Because that's what I think is creating a lot of confusion. You're only seeing it in how you would see it with respect to its ground position. There's not like two different perspectives of it. Does that make sense?
Yeah, no, I see what you're saying. So like, it's definitely good to know that there is a ground position of the sun. Is that it's similar to how I said they constructed the celestial sphere with multiple alt-az grids, literally people making the same observation within their limit of horizon from wherever they are on Earth. The same thing applies to the sun. You only ever see it in its apparent position, and then this sort of third-party orthographic position is extrapolated to get the ground position. So a bunch of local people make an observation on their local grid, and then they figure that out to get where the ground position of the actual sun would be. But again, that's never measured either. That's only ever calculated, and it's based on solar zenith at the equator.
Nice. That was a fantastic breakdown of the Gleason's map, bro.
Nice. I just want people to still like it's a tool, right? It's not broken. It hasn't been debunked in any way. Only people using it incorrectly and not understanding what it's showing, I think, can be debunked. Because again, these are all the same.
Yeah, you touched on it earlier when you said that to debunk one would be to debunk them all because none of them represent the ground. They all represent positions of the stars. Like that's the usefulness of it. It's not a it's not like they're all representing different things when they're under different projections. The purpose of this coordinate system is that it can be projected onto different projection types and still represent the exact same thing. So if you were to say that like one map is doesn't work because of a visual obscurity or something like that, that's a fundamental misunderstanding of the coordinate system itself and its usefulness, right?
100% couldn't agree harder, which couldn't agree harder, which brings me right into this, right? When people are comparing flight maps, flight routes, distances, lines of arbitrary length representing what they prescribe and pretend to calculate as different distances. So let's nip that in the bud. When we talk about flight paths, we are talking primarily of arguments of proximity.